So this course will be a blackboard course. There are no prepared jokes because my French accent should be sufficient for entertainment. It's a follow-up of the course of Ed Bertschinger last week. It's an introduction to the course of Shirley Ho next week, and it is complementary to what Bob Caldwell said on dark energy or what Leonardo Senatore will say on inflation. Okay, so what is the plan of the course? There will be, so I forgot the title, it's Cosmological Perturbations, and there is a subtitle for the end, and dark matter. So there will be a part 1 that will be an introduction to cosmological perturbations. And we will try to finish it today. The part 2 is a big part. We'll spend most of our time there. It's on CMB anisotropies. And my goal would be to convince you at the end of this part that the famous spectrum of CMB temperature anisotropies that you have all heard about can be simply understood as resulting from 8 effects. We will be very clear in identifying 8 physical effects. We will even call them C1 to C8, which controls the shape of the spectrum. This is the originality of this course, if you want, because usually people take a different focus. My dream is that by the end of the course, you can really see exactly what physics you can test with the CMB and which parameter you can measure or not measure. And I thought I would concentrate mostly on temperature anisotropy, but because there was a request, I will say a little bit also about polarization anisotropies and tensor modes at the end of this part. Then part 3 will be shorter. It will be the same for the matter power spectrum. Matter power spectrum. I will only discuss the basics, namely the linear spectrum of the minimal lambda CDM model. And similarly, I will try to convince you that this matter power spectrum has a shape controlled by 5 effects that we will call P1 to P5, following the same kind of decomposition of the physical effects. And this will be a preparation for the course of Shirley next week, who will go much more into details of impact of neutrinos or nonlinear corrections. Then we will be essentially done, but we will be happy to learn what we have, use what we have learned for practical purposes. And since you are mainly particle physicists, you are interested in dark matter, maybe also on dark energy, maybe we'll say a bit about dark radiation also. So the application in part 4 will be a summary of the constraints that we can have on dark matter, essentially on dark matter, a little bit on dark energy and maybe dark radiation from the spectra. We will discuss a case of a minimal cold dark matter model and of a few exotic candidates that would have additional effects. Okay, that's my plan. So if you are ready, willing to go, we start with part 1. Introduction to linear cosmological perturbations.
I think we should use a big laser there.
It's a big one.
Yeah.
Yeah, I feel much more powerful with this one indeed. Okay. Yeah, I'm Swiss, but I will not double clean everything. Okay, fine. So, linear cosmological perturbations. First, we will classify these perturbations. We will decompose all quantities, like for instance the metric, in the perturbed universe, as background quantities, G mu nu bar, depending only on time, plus perturbations, depending on time and space. And this is the metric of the Friedmann-Lemaitre model that you have studied already. You can do the same with any quantities, like the energy stress tensor. And in these tensors, since we are dealing with 4x4 symmetric matrix, you immediately recognize that there are 10 degrees of freedom. Way too much for practical purposes. They describe different sectors, different physical effects, and so it's useful to classify them. They describe, if you want, different aspects of gravity. And the classification, the most relevant one for cosmology, was proposed by Bardeen in 1980 in a very important paper. Bardeen showed how to decompose these two tensors into scalars, vectors, and tensor modes. And here scalar, vectors, and tensor are to be understood with respect to three-dimensional spatial rotation, so under SO3. And what is remarkable and not so obvious, given that the Einstein equation is nonlinear, is that the three sectors remain completely decoupled from each other at the level of perturbation theory, first order perturbation theory. So you can study them independently. And this has to do with the fact that SO3 is, of course, an underlying symmetry of the background of the Friedmann-Lemaitre model. Okay, you have to always remember, I start from very simple things that you all know, sorry for that, but it's always useful to remember that these different sectors have a very different status. Because if you are in the vacuum, then you can easily show from the Einstein equation that the scalars and the vectors vanish. Only the tensors do not vanish. They even propagate with the second order differential equation. So in this sense, the tensors are the only true physical degree of freedom in this problem, in these metric perturbations. They are the only ones that you can quantify and associate to a particle. The other modes are just response to matter stress. And indeed, in presence of matter, the vectors show you how the metric reacts to the presence of matter with a rotational distribution, with vorticity. So the vectors represent the response of the metric to vorticity. While the scalars represent the deformations of the matrix in response of a fluid that is irrotational. These kind of phenomena for the vectors are not covered at all by Newtonian gravity. They are called sometimes gravitomagnetism. In a given limit, the scalar perturbations are a generalization of Newton's gravity. Okay. In standard cosmology, vorticity decays. You can easily use the Einstein equation to show that in usual conditions, the vectors quickly go to zero. You need to work very hard with nonlinear phenomena, phase transition, etc., in order to generate a detectable amount of vectors. So we will ignore vectors in this course and focus on the scalars. And there will be a little bit about the tensors at the end of part 2. Okay, so if we limit ourselves to the scalars only, we have to deal with 4 degrees of freedom. Because among these 10, there are 4 scalars, 4 vectors, and 2 tensors. So 4 scalar degrees of freedom that I can represent schematically like this. Let me take my delta G mu nu, or indifferently my delta T mu nu, represented by a 4 by 4 matrix. Okay? There is a scalar degree of freedom hidden in the 0, 0 part. So the first one here. We'll give more details later. There is a second scalar degree of freedom hidden in the trace, in the diagonal part of the 3 by 3 spatial part. there is a third scalar function hidden in the vector, the three-component vector, which is here or here. In this part 3, I have a 3 vector, and this vector has an irrotational part, divergence part. And finally, in the traceless tensor which remains here, there is a fourth scalar function hidden in the irrotational divergenceless part of the tensor. Okay, now let's be more explicit, and we start by the example of metric perturbation. In this case, what is in 1 is the generalization of Newton's gravitational potential. So, we will introduce the gravitational potential, psi. This function psi will play the role of Newton's potential whenever you can neglect GR effects, which means essentially in cosmology on sub-Hubble scale. We are dealing with linear cosmology, so we are not thinking of black holes or anything like this. And Newtonian gravity is to be recovered on scale smaller than the Hubble radius. Then psi, this function, will be the gravitational potential. In this trace, there is a function which is easy to understand. It's a local distortion of what? If you plug here the background metric, what do you have in this part along the diagonal? You find the scale factor at the level of the background. So at the level of perturbations, we have a function here standing for local distortion of the scale factor. We will call this function phi of t and x. If phi is positive, it means that we are in a point in which, if you want, the local scale factor is bigger than average. It means that we are in a point in which the expansion of the universe is a bit anticipating over the average. If we are in a point in which phi is negative, it means, on the contrary, that in this point the expansion is like a bit late, a bit delayed. 3. 3 is one piece of delta J 0I that I can write as a gradient of some scalar function B. And 4, finally, is a part of delta J ij. It's actually delta G ij that I can derive from the operator di dj acting on a scalar function that I call mu. But remember that this part must be traceless, because a trace has already been encoded in phi. So I have to remove 1/3 of the Laplacian of delta ij of mu in such a way that this component is indeed traceless. And here are the 4 scalar degrees of freedom in the metric. This accounts for the shear part of the metric shear. Okay, we will see which role these components play in the following. We can do the same with delta T mu nu. For delta T mu nu, in the part that we called 1, we have simply density perturbations. In the background, I recall that the background T mu nu reads like this. T mu nu is equal to rho minus p minus p minus p, with some bars to remember that these are spatial averages. Okay, so at the level of delta T mu nu, what we find this is a density perturbation, delta rho. And here we define the dimensionless density perturbation delta, such that delta rho is equal to rho bar times delta. So delta is my relative density perturbation. We will usually use this variable. In the piece that we call 2, we have, of course, pressure perturbation, perturbations of this P. Pressure perturbations, delta P. In the part that we call 3, which is the part in delta T0I that I can derive from a gradient, we'll call this gradient V. This component accounts for energy fluxes, for the irrotational part of energy fluxes in my matter distribution. So irrotational energy flux. And in the parts that we call 4, that we can write, like for the metric, as delta Tij equal, and we use here the same traceless operator. So this part derived from a potential that I call S, and this represents anisotropic stress. Okay? When you have non-diagonal components in T mu nu, it means that you have anisotropic stress. We will see later concrete examples of how such a stress term can be generated. We could use these quantities delta P, V, and S as our perturbations. For purely reasons of habits, people introduce other degrees of freedom, but which are related to the previous ones. In particular, for instead of using V, people use a quantity called theta that we will define in the following way. Take now the divergence of T0I. So this is the Laplacian of V. But I can define that this divergence reads theta, which is another scalar function, and I put in factor rho bar plus p bar. It's absolutely equivalent to deal with V or with theta, since they are related just through a Laplacian and a factor. But theta is the one usually employed, and it is usually called the velocity divergence. Speaking of velocity here is a kind of abuse, because what it really represents is an energy flux. But if you deal with a fluid, this energy flux comes from bulk velocities in the fluid. So the theta is like the divergence of the bulk velocity of the fluid that you are describing. Why is this factor? First, because we wanted theta to be dimensionless. And why rho plus p instead of rho or p or something else? This is just to make the equation later a bit simpler. But some people use different conventions. Now, instead of using S, we will use also a different variable. The idea is the same. Take this operator and make it act on delta Tij. What you get can be easily shown to be the Laplacian of S, and we will define this quantity as the same factor rho plus p for the same reasons, time a quantity that we call sigma, and this sigma is often called the anisotropic stress, but in fact the real anisotropic stress is delta Tij. So sigma should be thought as a kind of potential giving rise to anisotropic stress. Okay, this was pure formalism. Now we have 4 variables describing the perturbation of delta T mu nu. Delta P, theta, and sigma. And they are all dimensionless except for delta P. That's all for this formal part. Do you have any questions? Okay, now we go to a more subtle issue, which is the one of gauge transformations. So, part 2, section 2, gauges. Why do we have to think in terms of gauge? Because in the perturbed universe, there is not a unique choice of time slicing for our space-time. And this is really easy to understand. Think first of a purely homogeneous Friedmann-Lemaitre universe. I will represent it schematically like this, with time flowing in this direction and space. I could represent, for instance, the distribution of the density of matter as with a gradient of colors. It would be easier with a computer, but I will use a computer only in the next lectures. Okay, I go from a very dense distribution of matter to an underdense distribution of matter. If the universe was purely homogeneous, there would be a preferred definition of time. Well, not of time, that's not true. There would be a set of preferred definition of time corresponding to a unique way to define equal time hypersurfaces. There would be a unique way to slice the space-time in uniform slices with homogeneous quantity on the slices. So in a homogeneous universe, there is no ambiguity about choosing a time slicing. This is not the case as soon as you introduce inhomogeneities. Suppose that I start from the same picture. But then I want to make the game a little bit more complicated and realistic. And on top of this, I had some local inhomogeneities. They are supposed to be small and not to violate the fact that this universe is nearly homogeneous in order to use perturbation theory. Now, there is not a unique way to choose my time slicing. There are many good time slicing. By good time slicing, we mean choices such as on each hypersurface, quantities are nearly homogeneous, up to linear perturbations. Of course, a time slicing going like this would not be a good one. It would mix points with very different background densities. But if my rule is only to be compatible with linear perturbation, I could use a given time slicing like this, or another one that I draw with a different color. They are all compatible with the idea that perturbations are nearly homogeneous, but there is no privileged choice. Now, if you think of how a perturbation is defined, let me define the perturbation of a density, for instance, delta rho of Tx, as the difference between the true density in a given point and its spatial average along one of these hypersurfaces. If I change my definition of the time slicing, this quantity is a true perturbation in one point. It will not change. Suppose, for instance, that I'm interested in delta rho in this point. It will be equal always to the same rho of Tx, which is a true matter density in this point, minus a non-local quantity, which is the average of rho along one of these hypersurfaces. If I am with a white choice, I will subtract here the average of the density along the white line. If I use the green choice, I will subtract the average along this line, and of course they will be slightly different from each other. So if I change of time slicing, this remains, but this changes a little bit, and all my perturbations are changed. So here we are dealing with a transformation which leaves the physics and the observable results invariant, so it's like a gauge freedom. Okay, so a gauge is a choice of time slicing. And gauge transformation, you see, are induced by changes of coordinates. In order to go from one time slicing to another one, I just need to specify a change of coordinates. So gauge choices induced by a change of coordinates, like this, with a vector field, epsilon mu, which has 4 degrees of freedom. So usually with this gauge transformation, or with, I can cancel 2 degrees of freedom in my problem. And in these 2 degrees of freedom, there are 2 scalars and 2 vectors. Because in epsilon mu, I have 2 scalars hidden. I have epsilon 0, and I have the divergence of epsilon I. And the other 2 are vector degrees of freedom. So now how do you deal in everyday life, in cosmological problem, with this issue? There are 2 approaches. You could try to deal only with gauge invariant quantities and equations. So this is a gauge invariant approach. To give an example, Bardeen showed how out of these 4 degrees of freedom that we call psi, phi, mu, and b, you can construct 2 independent functions that are called now the Bardeen potential, capital phi a and capital phi h, which are left invariant by a gauge transformation. You can also find equations acting only on gauge invariant quantities for gauge invariant metric or matter perturbations. And then you have a perfectly neat formalism, and you can forget about gauge issues. The second approach is much simpler. It consists in fixing a gauge. And by this we mean fix, not exactly a definition of time, but fix a time slicing. Take a prescription which fixes a unique time slicing. Usually this amounts in cancelling 2 degrees of freedom in the metric perturbation, but it's a bit more subtle sometimes. The real way to fix a gauge is to be sure that you cannot change this time slicing. If I fix a gauge, I do all my computation in a given gauge. I'm safe, because at the end of the day, I will compute observable quantities. By definition, these quantities are physical. They do not depend on the gauge. So the result that I found in one gauge applies to all gauges. So the results are always gauge independent. Gauge independent results. And this is simpler because you save the step of finding gauge invariant equations. We will use in this course this approach and stick to one of the most popular gauges, which is the so-called Newtonian or longitudinal gauge. In which the line element reads -1 plus 2 psi of dt square plus 1 minus 2 phi a square of t times, and here I have my spatial element dl square, which could be just a Cartesian dx square in a flat universe, or the more complicated function that you have already studied in the case of open or closed metrics. Okay, it's called Newtonian because it's easy to recover the Newtonian limit in this case. If you, under certain condition, psi and phi are equal to each other and stand for the Newtonian gravitational potential. It's also called longitudinal simply because it corresponds to a diagonal delta G mu nu. I can write this line element in terms of another definition of time, conformal time. This is not a gauge transformation. Redefining time does not change the set of constant time hypersurfaces. So a redefinition of time is something completely trivial. And if you use conformal time, you can write this metric as scale factor with respect to conformal time squared times this and so you recognize that we define conformal time as obeying to d eta is equal to dt over a. If I'm rigorous in my notations, I will try to use only a prime for the derivative with respect to conformal time, and a dot for the derivative with respect to proper time, to cosmological time, the time in which, at the background level, I get a 1 here, or a c² if I'm not in natural units. Okay, the Hubble parameter is, as you know, a dot over a. So in terms of conformal time, it's a prime over a square. Since we are talking of conformal time, it's a good point for giving you the condition under which a mode, a wavelength, is equal to the Hubble radius, because this will play a crucial role in the following. Okay, so time to play again with this eraser. So in the rest of the course, we will see that the first thing which determines the evolution of the cosmological perturbation is the fact that it is larger or smaller than the Hubble scale. This condition reads lambda, standing for a physical wavelength, equal to RH. I'm sure that you have seen RH in the last week or before. It is one of the two quantities with a dimension of space that you can build out of the Friedmann metric. There is a spatial curvature, and there is a Hubble radius, which stands for the radius of curvature with respect to time in space-time, RH and RC. So RH is C over the Hubble radius. Now, let's rewrite this condition in Fourier space. We will introduce Fourier space with respect to comoving coordinates x, which means that a comoving wave number will typically read 2 pi over k, but a physical wave number will be this comoving quantity times the scale factor. So this is the value of a given physical mode at a given time if it is described by the wave number k. This wavelength is equal to the Hubble radius when we have this equal to 1 over h. I work in natural units. Okay, and so the condition can be rewritten as k. I drop the 2 pi. K is of the order of AH, or I could write this as A prime over A. Okay, so a value of k larger than this corresponds to a wavelength smaller than the Hubble radius. This was a little digression. Coming back to the Newtonian gauge, it has another practical advantage apart from being diagonal, which makes lots of calculation easy. It's the fact that in the Newtonian gauge, the two barred-in potentials, phi r and phi h, which are in general combinations of phi psi, mu, and b, simply read phi m psi. It means that the solution that I will get in my Newtonian gauge solution are actually the same as I would get if I would work with gauge invariant variable. So it's a shortcut with which you avoid finding these gauge invariant equations. Now, you get 10 Einstein equations, since there are 10 perturbations, and out of these 10 Einstein equations, 4 deal with scalar degrees of freedom. I will not write the 4. Usually you don't need them because you know Einstein equations are redundant with Bianchi identities. So the Einstein equation will be used in many parts of the course as constraint equation, giving you phi m psi for a given matter distribution. So I will only use 2 of these Einstein equations. So the first one is the one dealing with the shear component of the metric and of delta t mu nu. This shear component tells you that a minus 2 k squared, because I am already working in Fourier space, so I don't have a gradient here, times phi minus psi is equal to 12 pi j times the sum over all the fluids of the anisotropic stress component, rho plus p sigma of my fluid. I is a label for the fluid. And this equation is interesting because very often we will deal with fluid with no anisotropic stress, with a very strong physical justification for this. See, if this is the case, if all the sigma i's are 0 or negligible, then you see that phi is equal to psi. And there is only 1 degree of freedom in the scalar metric perturbations. The other illuminating Einstein equation is the one for the 0, 0 component. It tells you that a minus 2 times k squared phi plus 3a prime over a phi prime plus a prime over a psi is equal to minus 4 pi j times the total perturbation of energy, delta rho tot, that you get by summing over the species. And now you can study the limit of this equation for modes which are inside the Hubble radius. So lambda much smaller than RH, corresponding to k, as we just said, much bigger than a prime over a. If I am in this sub-Hubble limit, the term with the factor k's will always win over the terms with the factor a prime over a. And this equation will simply reduce to minus k squared over a squared of pi equal 4 pi j delta rho tot. And bingo, you find a familiar equation, which is the Poisson equation. What is the difference between the Poisson equation that you... Oh, yes. So it's broken. Yeah. Okay. Thank you. Okay, the difference with the Poisson equation of Newtonian gravity is first that here we don't have just a Laplacian, but we have the Laplacian divided by a squared. This is because this Laplacian here is defined in comoving space. You need an a square factor in order to have here a physical Laplacian with respect to physical units. The other difference with respect to Newtonian gravity is that you don't have a total density, but it's perturbation here. But that's obvious. In a universe which would be unperturbed, there would be no gravitational forces. It would be all homogeneous. There would be no forces, no fluctuation of the gravitational potential. You need to depart from rho bar in order to generate forces, and this is why it's only delta rho which appears here. Finally, note that you might be disturbed by the fact that I don't have the gravitational potential here. I have phi. So in order to really interpret this as a Poisson equation, I need to be in a limit in which I also have phi is equal to psi. But this is very often the case. Yes?
Does the k squared include the time component of the Fourier transform?
Okay, so the idea is the following. Comoving objects have fixed comoving coordinates. Therefore, it is clever to define Fourier space with respect to comoving coordinates and to follow a mode with a given comoving wavelength, 2 pi over k. When you multiply by a, you naturally account for the expansion of the universe, okay, by saying that the real size of this mode follows the expansion of the universe. Is that okay? Yeah. Perfect. No question? Can we go to the next item? Okay. So, equations of motion. We will not give them in details, but we will sketch what will appear in the following. Equations of motion. We will deal with a variety of fluids described by different sets of equations. They can be placed on a scale going from the most strongly coupled fluids to the most weakly or even completely decoupled fluids or species. Decoupled fluid sounds ugly. Species. On the strongly coupled side, we will have baryons because they have strong Coulomb interaction, at least with electrons. On the decoupled side, we will have neutrinos and cold dark matter. And the photon will go all the way through recombination from the strongly coupled to the decoupled regime. So we will need to find an equation for gamma covering the two cases. Any equation of motion should be compatible with the Bianchi identities. Which are structural identities in gravity, saying that the covariant derivative of the stress energy tensor that I write with a capital D is equal to 0. So this gives me 4 equations for the 4 values of mu. The first one for mu equal to 0 is the equation of conservation of energy, conservation equation. I can write it like starting with delta prime, where delta is a total energy perturbation, equal to something, I don't have time to write it. In the little dots, there would be theta, there would be other perturbations, there would be coefficients depending on the equation of state and the sound speed of the species. I have 3 more equations. One of them stands for a scalar degree of freedom, for an irrotational part. This is the Euler equation, which I can write as the equation of motion for theta. And then I have 2 equations for vectors. What about individual species? This is for the total fluid. If individual species are decoupled, they will satisfy the same equation. Otherwise, they will satisfy d mu t, say A mu nu, where A is the level of my fluid, is equal to a coupling term, Ca. And because I want to satisfy the Bianchi identities, I must impose that the sum over all species of the coupling coefficients do vanish. Now, for rich fluids, we just say that we have immediately here 2 equations available, conservation and Euler. So 2 equations, but we have 4 variables, which are delta, delta p, theta, and sigma. Yeah, you are right, sorry. Yeah. So we have 2 equations, 4 variables. It looks like the system is over-constrained. Is it really over-constrained? No, this is enough if we deal with perfect fluid. Why? Perfect fluids are strongly interacting. So the mean free path in the fluid is negligible. This immediately tells you that you cannot generate an isotropic stress. Because sigma different from 0, and an anisotropic stress could be generated only if you have anisotropic pressure. So once and for all, is it anisotropic or anisotropic? Oh, you know. Anisotropic. Okay, thank you. Okay, sigma different from 0 can be generated if you have anisotropic pressure or different flows of matter. If sigma is different from 0, it means that an observer in the fluid would feel different pressures when he looks in different directions. So this is anisotropic pressure. This is usually the case if in a given point you receive different flows of matter from different directions. Suppose that we look at neutrinos. Neutrinos are decoupled. So if I sit here at a given time, I could very well see a flow of neutrinos coming from one direction and a flow of neutrinos coming from another one with a different velocity. I will perceive this as an anisotropic pressure. Okay. If I have a perfect fluid, strong interaction maintain a real pressure, which is isotropic, which is just a given number in a given point, and there cannot be different flows because my interaction also imposes a bulk velocity. In a given point, particles can be described with a unique bulk velocity. So this cannot be achieved in a perfect fluid. Second, if I have a perfect fluid, I know that my pressure will obey to an equilibrium relation of the type delta P equal the sound speed square times delta rho. Actually, for this it is sufficient to have a barotropic fluid, but perfect fluids are a subcase of this. Okay? If I know the density in one point, then I know the pressure through this coefficient. So, in perfect fluid, you get rid of this degree of freedom, and this one is a function of this one. So we have two equations and 2 degrees of freedom, which are delta and theta, and we are done. These 2 conservation and Euler equations are sufficient. This is for perfect fluid, but it's not the case in general. Yes? Yes. Barotropic fluid is a fluid in which the pressure in a given point can be entirely computed as a function of the density. So there is a subtle difference, which is not very relevant for us, but it can be relevant, very relevant in thermodynamics. Perfect fluid is defined as a fluid in which you can neglect the mean free path. So then, after some work, it shows you that you have a unique value of pressure and a bulk velocity. The theory of imperfect fluid is quite interesting, but it's completely out of the range of this course. And perfect fluid are just one limit of this theory, corresponding to very strong interactions. Okay. Now, in the general case, I cannot get rid of 2 of my 4 degrees of freedom, and I have to use a different formalism. This is a case for decoupled or weakly interacting fluids. In this case, we will have to introduce the phase space distribution for the fluid A and use the Boltzmann equation giving its evolution. So the Boltzmann equation tells you that the total derivative of the phase space distribution with respect to time, here is conformal time, so this is a Liouville operator, which can be expanded in partial derivatives, is equal to a coupling term. The coupling term for the species A, which depends on the phase space distribution of A, and that of any other species with which it is coupled. Okay? So this Boltzmann equation is much more general than just a conservation and Euler equation, even if it usually contains these 2 equations. And for us, it will be useful when we will describe in particular photons. So Fa, the phase space distribution function, is a function of time, position, and momentum. And in our context, we will decompose it into a background phase space distribution function only of time, plus a perturbation that is a function of all the other variables. Now, we have 2 limits here. Perfect fluid, strongly coupled, and weakly coupled fluids. Where should we place cold dark matter? Cold dark matter is assumed to be decoupled at all times of interest for CMB physics and large-scale structure formation. Okay, cold dark matter, depending on the model, can decouple at different temperatures, but they are all much higher than the one of interest for computing the CMB. So cold dark matter is decoupled. We should describe it with an equation of this type. In fact, we don't need that, precisely because cold dark matter is cold. and this is very easy to understand. So cold dark matter is a model in which the particles decouple when they are non-relativistic, and then their phase space distribution that you can compute for WIMPs or any other model tells you that the velocity dispersion or the momentum dispersion of the particle is very small. So schematically, I can represent it like this in phase space. I take only one dimension for the velocity, one dimension for space. And in phase space, my cold dark matter particle, in average, obey to some distribution which reflects the Hubble flow plus some perturbations. The fact that dark matter is cold means that the velocity dispersion that you would expect to observe in principle around this mean value, and which is related to the shape of the phase space distribution, is negligible with respect to the average value. So cold dark matter occupies a very, very thin layer in phase space. In this case, everything is as if you had a single flow of matter. By this I mean that if you look at the velocity in a given point, the bulk velocity here is approximately equal to the peculiar velocity of each individual particle, because you don't observe small differences. So it's like if you had a bulk velocity. Moreover, the pressure usually is related to the kinetic energy of individual particles, and so it's related to the square of the velocity dispersion. So the pressure for cold dark matter is negligible. So at the end of the day, I still have delta P fixed to something, which is 0, and I still have a bulk velocity which forbids any anisotropic stress. So this is effectively equivalent to a perfect fluid with a sound speed square delta P over delta rho equal to 0. This is true only at the level of linear perturbation. When cold dark matter start to form nonlinear structure, then this line will start to fold over itself because of gravitational attraction. If I have a collapse here around an overdense region, in this case, at a given point, I can have different flows of velocity. Then I develop an isotropic stress, and I cannot use this trick anymore. Okay, that's all what I wanted to say about equations of motion, and we will see later some more specific examples. Yes?
I have a question between the Boltzmann equation and the conservative equation.
Yes.
The collisional term is related with the C, vector C that you have in the...
No, here it's a different one. It's not a vector. Here it's not a vector. It's just a complicated function of the phase space distributions that you can find.
Somewhat related?
Yes, of course they are related, because if I integrate over some momenta of this equation, I will reproduce my Bianchi identity. And so the C which is here is like the integral over a momentum of this C with some momentum factors in front. So I can find the relation here. Yes?
I just wondered, because under the cross went to this change the Koenig gauge,
Yes?
reduced the 4 degrees of freedom to 2.
Yes.
But now when we're studying the equation of motion, we've had back to 4 degrees of freedom now.
Ah, very good, very good, very good. Yeah, no, I've not been clear enough that when you specify a given time slicing, a given gauge, you get rid of degrees of freedom in the metric. So degrees of freedom in delta T mu nu are always there. It depends really on the physics of the fluid. Other questions? Okay, we arrive to a fun part, that of initial conditions. Initial conditions can be very tricky. There are infinitely many ways of explaining this. I will try something that hopefully will be concise and clear. You will judge. And we cannot make the economy of this discussion because all the results will be based later on the fact that we use the famous adiabatic initial condition. So 4 is initial conditions. Okay. We are going to follow our Fourier modes. We will draw lots of plots like this with time running from top to bottom and wave number running from left to right. A mode crosses the Hubble radius when k is of the order of AH. This is Hubble crossing. If I draw the line corresponding to k equal to AH, assume this is log-log space. I will find a line which is qualitatively like this, meaning that larger k, which are smaller wavelengths, cross the Hubble radius earlier. So the idea is that the modes that will give rise to CMB anisotropies will be taken initially outside the Hubble radius in this course. When you will study inflation, you will go further up and you will see that things are different. We will fix initial condition outside the Hubble radius because this is when I can use simple initial conditions derived from first principles. And then starting from this line, my modes will evolve. So these are co-moving wave numbers, and they will undergo some complicated physical evolution. At some point, a given mode will enter inside the Hubble radius corresponding to crossing this line. So we fix initial condition in the super-Hubble region where k over AH is by definition much smaller than 1. Yes, this line is where k is AH here. Okay, what are we talking about? About the fact that we have many degrees of freedom, many perturbations. We have 4 for each fluid, sometimes 2 when it's perfect fluid. We want to solve for all these evolutions, and since I have so many degrees of freedom, then maybe I have infinitely, not infinitely, but many, many possible sets of initial conditions. I want to convince you that a very restricted set of initial conditions is more appropriate, or at least more likely in our universe. So this is the topic of the discussion that will follow. I'm going to say something. It's a claim which is very important in many contexts in cosmology. It's always good to have it in mind. In the super-Hubble, so modes with a wavelength larger than Hubble radius, in the super-Hubble limit, I infer from first principles that T mu nu, delta T mu nu, the perturbed T mu nu, must be diagonal, which restricts also, of course, the possibilities for the initial delta T mu nu. This can be shown in very different ways. It's a deep statement. It tells you that the physics outside the horizon is very similar to the physics describing the background evolution. Let me be a little more explicit. Suppose that I solve fully for my equation. I compute delta T mu nu as a function of time, and I expand this delta T mu nu. I expand it in powers of k over AH. And this is a quantity which is very small outside the Hubble radius. Let's consider the first term in this expansion, the term at order 0. The term at order 0 corresponds to delta T mu nu in the limit of a vanishing k. So it's a 0 mode. A 0 mode is evolving like the background. In fact, it is the background. Okay. Now, the background T mu nu must be diagonal. You know this form, and probably you remember why it must be diagonal. I don't know if Ed explained it in details or not, but being diagonal is a condition for being compatible with the assumption of homogeneity and isotropy. So at order 0, the zero mode component in my delta T mu nu must also be diagonal. And so it will read, at order 0, it will read delta P, delta rho minus delta P minus delta P minus delta P. And zeros elsewhere. Otherwise, we are not dealing with a statistically homogeneous and isotropic universe. You could push the argument, we won't make it, but you could show that at order 1 there is a term growing with time, like k over AH. And in this term, you will find the degree of freedom theta. So theta, which would contribute to these components, is initially 0, but it grows slowly outside the Bell radius, and it contributes to the first order term in this expansion. At order 2, you would find a term even smaller, but also growing with time, and this term would contain the anisotropic stress. This is rather intuitive because in the way we define theta and sigma, you saw gradients. You saw one gradient for this part and two gradients in this part. Of course, when I deal with super-Hubble fluctuation, gradients are negligible. And this term is suppressed at order 1, this term is suppressed at order 2. Why is it important in this context to know that at order 0, delta T mu nu is diagonal? Because it means that in my initial condition, I can start from theta is equal to 0, sigma is equal to 0, and I just need to know for each of my fluid what is the value of delta rho and delta P initially. Okay? So, initially, if I have n fluids in my universe, n components, and I assume that I know for each of them delta P over delta rho, which is the sound speed. In practice, it is always the case. I have n fluid with n known sound speed. Then for each fluid, the only uncertainty in the initial condition is about delta rho. So the basis of possible initial conditions is a set of delta for each fluid. So n numbers. This is already a big restriction. Next, among all these possible initial conditions with an n-dimensional basis, I want to tell you that one subset is special. Plays really a particular role. And this is very intuitive. Let us think of how we can construct an inhomogeneous universe. And let us start from the solution for the homogeneous universe. We are able to fully understand the homogeneous evolution. For each fluid, we can compute the evolution of the background density and the background pressure. Now, one way to understand a particular perturbed universe would be to say, let's take a homogeneous universe, and in each point that will give rise to a word line, we shift the evolution by a shift function, delta t of x. Which means that, for instance, rho a of t and x is equal to rho bar of A of T plus delta T of X. This is a very powerful, very restrictive assumption. I'm assuming that all my quantities are perturbed because I shift the initial time from one point with respect to another point. It doesn't have to be the case for all perturbed universes. It's an assumption. Delta T would be the same for all fluids and all quantities. For instance, for pressure, PA of T and X would be given by PA bar of T plus delta T and X. Okay, physically, this will happen if my universe is perturbed initially by a single degree of freedom that plays the role of a clock and that depends on space. this will be exactly the role of the inflaton in inflation. It's a single degree of freedom, which initially changes the time from one point to another point. If I make this assumption, I get lots of non-trivial results. First, if I Taylor expand this quantity, I get that this is equal to rho A bar plus, and I Taylor expand with respect to t, plus rho A bar point times delta t. For the pressure, it's the same. It's equal to P bar plus PA bar point delta t. Now let's play with these relations and see what they imply. First, let me compute delta t as a function of the rest. Delta t from this relation is given by rho minus rho bar. What is rho minus rho bar? It's delta rho. It's delta rho of my fluid A divided by rho A bar point. Now, on the right-hand side, if I use the conservation equation that probably you have seen in the course of Bertschinger, here you have a minus 3 A prime over A times rho A bar plus PA bar. Let me put this quantity on the left-hand side. I get that minus 3 A bar over A delta T is equal to delta rho A over rho A plus PA. But what is important is that this quantity is the same for all species. I have a unique delta T in my problem, a unique scale factor. So this is true for any A. So what it means is that in such a universe, for any pair AB, I have delta rho A over rho A plus PA bar equal to delta rho B over rho B plus PB bar. So I have a relation between all my perturbations. For instance, if I consider the case of the photons, baryon, and CDM that we will discuss later, what is this quantity for photons? I divide the numerator and denominator by rho bar A. So I get delta for the photons equal to 1 plus PA bar over rho A bar. For photons, which are a relativistic species, the equation of state is 1/3. This will be equal to the same for baryons, especially that now the equation of state is 0. CDM is also non-relativistic. If I want to have neutrinos, they are relativistic. They have an equation of state of 1/3. So this is 4/3. So this shows that if these conditions are satisfied, I should start from 3 over 4 delta gamma is equal to delta B is equal to delta CDM is equal to 3 over 4 delta nu. So I could relate all perturbations to each other, and I have only one free number now for fixing my initial condition. For each mode, if I give you the initial value of delta gamma, you know all the initial conditions for all perturbations. Let's gain some physical interpretation on these quantities. Suppose that I compute delta PA over delta rho A. Using these equations, you see trivially that this will be given by PA dot over rho A dot. P dot over rho dot in thermodynamics, in hydrodynamics, is called the adiabatic sound speed. So if such conditions are satisfied, then my fluids have an adiabatic sound speed. I'm still working in the limit where K over AH is very small, by the way, since I'm considering a diagonal delta T mu nu. So this initial condition should be thought when I'm very far outside the Bell radius. Then in this limit, each my fluid must have an adiabatic sound speed. And a stronger result is that, and we will have to finish this section before going to lunch, because the end is scheduled at noon, right? Okay. Okay. Okay, but I will not exceed too much. Okay, the second result that you can infer from this relation is that if you compute the total delta P, by summing over the delta P's of all species and using these relations, you easily find that delta P is related to delta rho tot with the factors that you can express as a weighted sum of the adiabatic sound speed of each fluid. You can do it as an exercise. What is non-trivial is that this factor is independent of space, just and time, just a number. Okay, so with such initial condition, this relation is satisfied, and it means that my total universe looks like filled with an adiabatic fluid, because this is the definition in hydrodynamics of an adiabatic fluid is that it has an adiabatic sound speed like this. So these initial conditions are called adiabatic initial conditions. But what is truly fundamental about them is this way to construct them. Okay. This relation would not be true in general. We should insist on this. In general, if we don't start from such restrictions, we will find that delta P tot is simply the sum over all fluid of Ca square delta rho A. And you cannot reduce this to this form. If you try to have delta rho tot appearing, you can always do it. You can always rearrange the term in such a way that you will get here the sound speed squared times delta rho tot. But then you will be left with n minus 1 other terms that I can write in the following way. I can write them as plus a sum over coefficients DAB, and I will define this, times SAB. So what are these coefficients? And the sum runs over all A different from B. This is formally how I can write delta P tot in general, by expanding over all degrees of freedom in the fluid. So here we have arbitrarily chosen a reference fluid with an index B. We could choose any of them. So B is the index of a reference fluid. SAB is defined as the difference between the terms that would be equal with adiabatic initial conditions. Delta rho A over rho A bar plus PA bar minus the same for B. So this difference is non-zero in general. It's called an entropy perturbation. It's like a shift between the internal degrees of freedom of the fluid. So this is an entropy perturbations. And these are n minus 1 coefficients that will be non-zero if I don't start from adiabatic initial condition. So in general, I have one adiabatic mode plus n minus 1 entropy modes. But you see that a condition, a necessary condition, not sufficient, for generating entropy modes is to perturb initially your universe with 2 degrees of freedom. So for instance, you cannot do it if perturbations are due to single field inflation. But if perturbations are due, for instance, to double field inflation, then you can introduce initially 2 shift functions, delta T1, delta T2, independent of each other. Then you cannot reduce the initial condition to the adiabatic forms, and you will have some non-zero coefficient DAB. Maybe you heard about isocurvature modes. Isocurvature modes are just another way to define the basis of initial condition. I could combine my adiabatic mode and entropy modes into another basis. It's just a linear change of basis with one adiabatic mode and n-1 isocurvature mode. What are these modes? Isocurvature modes are a choice of initial condition such that asymptotically, very far outside the Bell radius, the total curvature and perturbation in the universe vanishes. You can arrange isocurvature modes by assuming that, for instance, all initial perturbations are 0, except the perturbation in two fluids which are opposite to each other. So that you have non-trivial perturbation in the fluid, but they do not generate curvature perturbations initially. Now, why people usually focus on the adiabatic mode? First, because it's simpler to assume that initial perturbations are generated by a single degree of freedom. But moreover, there is something else. Assume that you have your different degrees of freedom, for instance, with double field inflation. Initially, you generate, say, one adiabatic mode and one or several entropy or isocurvature modes. Assume that all particles later are in thermal equilibrium. If you have thermal equilibrium, then all densities are related to temperature. And in a perturbed universe, temperature will be a function of T and X. So it will be equal to a background temperature times some fluctuation. These fluctuations are a single degree of freedom with respect to which all perturbations are related. It plays exactly the role of the shift function. This shift of temperature is related, you can even find the equation relating it, to the shift function. And then all the relations that we saw here will automatically apply, and it means that thermal equilibrium kills any entropy or isocurvature modes generated previously. So if you want to have detectable entropy modes today, you need several conditions. First, you need these several degrees of freedom. Then you need to assume that the species carrying these entropy modes are forever decoupled throughout the evolution of the universe. If cold dark matter carries entropy perturbation and never couples, then they will be preserved. Or another trick is to assume that the species is in thermal equilibrium, but with some non-trivial chemical potential. The degree of freedom mu, the chemical potential in a thermal phase space distribution function, could be perturbed, could carry isocurvature modes, and this mu would not be erased by thermal equilibrium. It's like adding a second degree of freedom here. It's a subtlety. You don't need to remember this. It's only if you are interested in this. The message is that it's very difficult to meet all the conditions for having entropy modes surviving until today. And moreover, ultimately, the observations are the ones that should decide. And so far, they are compatible with pure adiabatic initial conditions. There are very strong limits on isocurvature modes from the CMB. I would like to make final statement in 1 minute, and I take your question. No final statement. Okay. Question. So in principle, these other modes could show up in the CMB or in the matter power spectrum, in any observable related to the perturbations. And they would have different shapes, different features. So the strongest conditions that we have are from combination of CMB and matter power spectrum, but they are dominated by CMB constraints. Yes. Decoupled means that the species with the entropy mode should never reach its thermal equilibrium. So a good example would be axions. Axions are a candidate for cold dark matter, which are always decoupled. So the model in which axions are the cold dark matter or part of it is a natural candidate for isocurvature modes. So axions, under some assumptions, can be constrained through the study of signature of isocurvature modes. But so far, we have only upper bounds, no detection. Okay, so as usual, we have been a bit slow with respect to the schedule, but it doesn't matter. I mean, it cannot be faster than this, otherwise you wouldn't like it. So next time we take 10 minutes to finish the introduction, and we start with the CNL.